Timo Seppalainen, who I've known for so many years, an old friend. He's speaking from the University of Wisconsin at Madison, and he'll be talking about stationary horizon as the universal multi-type stationary distribution. So please. Oh yeah, by the way, Timo has also provided the slides and a handout for the talk, which I put in the chat. I don't know if everybody can see that. So one can follow along if one would like the handout or the actual slides themselves as he goes through them. Okay. So thank you, Timo, and please proceed.
Okay, yeah, thanks, Sunder, and thanks to all of you who organized this thing. It's nice to see familiar faces for a change. All right, so the topic of the talk is the stationary horizon. And by the way, are you hearing me well enough?
Yes, right. I hear you very well. Everybody else?
Okay, thank you. Let's see. All right, so what is the stationary horizon? It's a certain stochastic process, and it has come up in various places in the KPZ picture. So my goal here is to introduce you to this object and to show you how it appears in the directed landscape, and hoping that there's time left in the end and also in the TASEP speed process. So this is joint work with Ofer Busani, who is transitioning from a postdoc in Bonn to a faculty position at Edinburgh, and Evan Sorensen, who is about to graduate here in Madison and on his way to Columbia for a postdoc. All right, so I'm going to begin by introducing the directed landscape. The directed landscape can be defined in terms of the area line ensemble, but rather than go that route, I'm going to introduce it as the scaling limit of a familiar concrete object, namely the corner growth model, which I think is fairly well known to just about everybody in this audience. So here's the corner growth model. We put random weights on the vertices of the planar square lattice. Those are the omega x's, and we take them to be exponentially distributed. And what we look for are increasing paths, like in the picture on the left. Gamma is a path that connects those two vertices, u and v. And what we do is we calculate these last passage values. So the last passage value L for u and v is the maximal amount of weight collected by a path from u to v. And we are also interested not just in the values, but also in the maximizing paths. We call those geodesics. And with an exponential distribution, like with any continuous distribution, there's almost surely a unique geodesic. So I'm being pretty brief here. Is the description of this model sufficient, or have I omitted something that leaves anyone there confused? So please feel free to interrupt anytime something should be clarified. Maybe not. All right. So there's the definition again. And the question is there a scaling limit for this entire field on the plane? And the answer is, of course, yes, known since the monumental work of Duncan and Janos and Balint. The limiting object is the so-called directed landscape, which is a 4-parameter random field. And it's expected to be a universal limit of all these last passage and other models in the KPZ class in this so-called 1, 2, 3 scaling, which means that we take time increments of order n, spatial increments of order n to the 2/3, and then we see fluctuations of order n to the 1/3. And I'm going to illustrate this with a picture here. Here's how we scale the corner growth model before taking the limit. The time direction is now the diagonal. You can choose some other vector also, but you have to go into the interior, into the bulk. So you see we go, do you see my cursor, by the way, if I wiggle it around here? Okay, thank you. Yeah, so we go order n in the time direction here, and then we deviate from this diagonal at order n to the 2/3. That gives the spatial variables. So see, there's the x and there's the y. And then we center appropriately, and then we divide by n to the 1/3, and we get a limit. So here it is in terms of a formula. There is the last passage value and the appropriate centering, and then the n to the 1/3 normalization. The details of this limit are not important. I just wanted to show this for the sake of completeness, to give us a route to the directed landscape. If you're wondering where this centering comes from, some of you probably remember well the shape function of the exponential last passage percolation model. So this centering is what you get when you expand that shape function and you throw away all those terms that go to 0 in the limit. All right, so let's take now the directed landscape for granted. Let me list a few of its basic properties that are good to keep in mind. So it is a random continuous function on its domain. So the domain is this set of directed space-time points where the time coordinates are strictly ordered. And it is itself, of course, an instance of last passage percolation, but now in the continuum. So this kind of a formula is valid. So if I go from time level S to time level U, but then I stop in the middle at time level T, then I maximize over the spatial location. So there's the LPP property. And of course, we can then define geodesics again. A geodesic would be a path that maximizes in this value, in this formula here, at all the intermediate time points. So in particular, if I take a partition of time, then the directed landscape value from the beginning to the end of the path is the sum of the intermediate increments. So this would define a geodesic, and it's a fact that these geodesics exist between any 2 points. So that's the basic setup. And now I want to ask about something a little less trivial, namely about semi-infinite geodesics. So a semi-infinite geodesic would be a path that starts somewhere and goes on forever into the positive time direction. And it has the property that it's a geodesic between any 2 of its points. So now there's real questions here. Do such a things exist? Do they have directions? If one exists from a point to a particular direction, is it unique? And then how do they interact with each other? You know, do they cross each other? Do they not see each other? Do they maybe coalesce? So these sorts of questions have been pursued for these growth models for several decades now. So they're well-known questions. So let me begin by answering some of them. So Mustaseraman and Balint-Virag gave a start here. They proved various things under a fixed direction xi. So in particular, they showed that every initial point has at least one semi-infinite geodesic in that direction xi. So by the direction, I just mean that this path has a limiting speed given by xi. And they answered the uniqueness question. If you fix the direction and you fix the initial point, then this semi-infinite geodesic is unique. And then they also established the coalescence, again in a fixed direction. So if you take any 2 geodesics going in that particular direction xi, then with probability 1, they do coalesce. But now the with probability 1 statement depends on the direction. So the next question is then, what happens if we don't fix a direction, but we simply pick a typical realization of the directed landscape, and we ask these same questions and we try to say something simultaneously across all the initial points and all the directions? So there's sort of a game of null events here, in a sense, which null events you consider and which you don't. So I want to try to answer some of these questions now, and along the way, I'll introduce the tool that we use, which is this so-called Busemann process. So I'll turn to that Busemann process next. So a first step in the construction of a Busemann process is to establish individual Busemann functions. So these are objects for a fixed direction. And this again comes from Mustase's and Balint's paper. So give me a fixed direction, and they prove that this limit here exists almost surely for all these initial points x, s, and y, t. So if you're seeing this for the first time, let's inspect this a little bit. So you're fixing this direction zeta, and you're going infinitely far into that direction, and you're looking for the difference of the two these two directed landscape values. So you're, in a sense, kind of differentiating. This is a subtle limit because you're not normalizing by anything. So the randomness persists all the way to the end. So this W thing is a random thing. So Mustase and Balint established this. And now the next step would be to construct this thing simultaneously for all the directions zeta. Well, there are uncountably many of them, so you can't really rely on this limit for the full thing. So what you do is you first take this limit for a dense set of directions, say for all the zetas that are rational, and then you take advantage of properties that hold on the plane. So in particular, if you arrange those points x, s, y, t in a particular manner, you will have monotonicity in the zeta parameter. So you can build on this and other properties and establish that you can actually take left and right limits in the zeta parameter. And you can take these limits, they exist almost surely. So here they are, and let's call them wc minus and wc plus. So now we have this object defined for all directions, and we'll call that the Busemann process. And so you see now it's a process that's indexed by directions xi, these signs plus minus, and then these pairs of space-time points. And it's particularly important then to have this distinction to xi minus and xi plus. So it's actually convenient to keep them both alive, so to speak, because looking at these jumps actually gives us a lot of useful information. So my contention was that this object is useful for studying semi-infinite geodesics. So let me show you a little caricature just to suggest why that would be the case. So this is going to be a little picture just drawn with a plain hand. And the point here is just to give you an idea why the jumps of the Busemann process might have any significance. So look, in this picture, I've taken three directions, a zeta, an xi, and an eta, and two space-time points down here, p and a q. So in the zeta direction, I've drawn these semi-infinite geodesics, and I've made them coalesce. So z zeta is the point where the red geodesics from p and q coalesce. And the same thing is going on here on the right in the eta direction. The eta-directed geodesics from p and q coalesce at this point z eta. So this has the effect that when I calculate the limit, the Busemann limit into the directions zeta and eta, I don't actually have to go all the way to the limit. I just need to go until the geodesics coalesce. So that's what is expressed in these formulas here. But the xi direction is sort of a bad direction. See, I've drawn two semi-infinite geodesics from p in direction xi. So the idea here is that there's non-uniqueness there. Two xi-directed semi-infinite geodesics from p. And now let's see what effect that has. Imagine now that you let the zeta direction converge to xi from the left, and you let the eta direction converge to xi from the right. So what do you see? Well, these geodesics, they are sort of nicely ordered. So this red geodesic in the limit, it will just sort of slam into this left xi geodesic. And these blue geodesics from the right, they'll just slam into this right xi geodesic. And the net result is that the W values in the limits cannot coincide. So this way, this at least suggests that these jumps of the Busemann process, they carry information about the geometry of the geodesics. So once we accept this, now the task is to try to understand something about the the Busemann process. So in particular, let's try to see if we can capture some information about its distribution. So as a first step here, I've done a little calculation, the only calculation in this talk, where I illustrate how the Busemann function evolves on the plane. So the very first line at the top is simply the definition of the Busemann function in direction zeta, the same thing that went by a couple of slides ago. The second line uses the last passage percolation property of the directed landscape. So here, on my way from time level R to time level U, I've stopped at time level S and maximized over the spatial location Z. So that's this so-called metric composition property of the directed landscape. On the third line, I simply slip that limit inside the supremum and then recognize that this limit is, of course, another instance of the Busemann function. So that's on this last line here, the W thing. So in other words, these W functions evolve backward in time, according to this formula. And now the salient feature is that the two objects inside the brackets there are actually independent. And the reason is that the one property of the directed landscape is that the values are independent over disjoint time intervals. And that's what we have here, R to S and then S from S to infinity. So we have independence inside there. So this means that there's a Markovian evolution going on. And this evolution is actually something quite important in the KPZ picture. This is the so-called KPZ fixed point, just with the twist that it's going backward in time. So let me tell you a few things about the KPZ fixed point, just one slide's worth here. A couple of things that we need to know. So the KPZ fixed point was the earlier introduced universal object in the KPZ class. It came in that other monumental work, this one by Matetsky, Quastel, and Remennik. They constructed this process by taking a limit of Taset, and they described it in terms of determinantal transition probabilities. And then in a subsequent work, they connected it with the directed landscape. So it turns out that the KPZ fixed point, which is a Markov process on functions, it can be realized by running this sort of a Hamilton-Jacobi semigroup in the environment provided by this directed landscape here. And this is, of course, hugely useful because this allows us now to couple the KPZ fixed point from various different initial states and just put them all on the same probability space with this variational formula. So let's summarize things a little bit here. So our goal is now to find the joint distribution of the Busemann process. So I want to take n direction values and look at the W functions indexed by those directions. They're all continuous functions. So this thing here is itself an element of n tuples of continuous functions. And I'd like to understand the distribution of this object.
May I ask a question?
Of course.
So let me just try to understand. So you have the directed landscape. So it's this process in R4,
yep.
And it should have some sort of Markovian property. But I'm trying to figure out where are the lines on which you have to condition to get independence or things like that.
Well, you look at the so if you think back at the last passage percolation limit, if you look at disjoint time intervals, then the L values are independent. Mm-hmm. If you confine the L values to one time level time strip and then a disjoint time strip, then you have completely independent values.
Okay, thanks.
Okay, so we know a few things about this W thing. I just kind of showed you that it evolves under the KPZ fixed point.
So to interrupt you again, the Timo.
Yeah,
it's just that. Okay, so just like a cake recipe. So if one thinks about the Markovian property of the last pass of percolation, this type of Markovian properties, they don't get destroyed by taking the limit. So they survive in the limit. That could be like a way to understand what are the bits which are independent between them.
I guess I'm not sure now what you are saying. Sorry.
No, it's because in the last part of the percolation picture now, I mean, if you do things like drawing a line on your lattice, and then knowing what are the values above and below. I mean, you know that
I see. So you're wondering if the structure is inherited.
Yeah.
Presumably, yeah.
Okay.
All right. So we know now a few things about this W. We know what the distribution is if you fix a time level. So individually, if you fix t and you fix one point the origin and then let this x vary here, you have a Brownian motion with drift. So this, for example, comes from some work of Leandro Pimentel and from other places too. And furthermore, this W thing is translation invariant in space-time. And that has to do with the translational invariances of the directed landscape. So with this in mind, we have the following task now. We'd like to find a multifunction joint stationary distribution for the KPZ fixed point. In other words, an n-tuple of functions, each of them evolving under the KPZ fixed point, but so that the distribution is preserved. That's what this line here says. Now, when you evolve under the KPZ fixed point, there's an overall height shift along the way. So that's why you have to renormalize by subtracting something. So what you're really saying is that the object whose distribution is preserved is the spatial increments, okay? And then if we can prove a uniqueness theorem, something along the lines that if such and such holds, then this is the unique distribution, then presumably we have the right thing in our hands and we know that this must be the distribution of the this Busemann process. All right. So now I'll just give you the answer. The answer is this object called the stationary horizon. And what is that? So it's a cadlag process indexed by the real line, and the states themselves are continuous functions. So this is the path space, the D space of CR valued paths. And here's a recipe for constructing its finite dimensional distributions. Take a bunch of independent Brownian motions with drift. And by the way, of course, I've made certain choices here, certain conventions. I've made the diffusivity square root 2, and I've put a factor of 2 in front of the drift. These are all just to make things work out in the end, right? So take those independent Brownian motions with drift. Then this n-tuple of stationary horizon values can be realized, distributionally realized, as a deterministic function of these Brownian motions. And what are those functions, psi2, psi3, psi4, etc.? Those are Brownian last passage values, or equivalently queuing mappings. Here's a formula. Again, the details don't matter much. For those who are well-versed in queuing or last passage kinds of things, we'll see that immediately that it's familiar. And for those who don't, it's not of much importance. The point just is that the stationary horizon's finite dimensional distributions come from a mapping of independent Brownian motions. What are its immediate properties? That mapping preserves the marginal distribution of individual functions. So each value of the stationary horizon, when you fix the index C, it's a Brownian motion with a drift again. And then if you fix the X, the spatial variable, and let the C index vary, what you get is a jump process, a non-decreasing jump process if you order the spatial variables correctly. And in the very next slide, I'll show you a picture. Now, where's this coming from? The story is sort of moderately intriguing. So Ofer Busani first derived this object by taking a diffusive limit of the Busemann process of the exponential corner growth model. And this interesting name is from Ofer's brain. Now, meanwhile, Evan and I were studying the Busemann process of the Brownian last passage percolation model. And then in October 2021, Ofer's paper came on arXiv. And after a moment's perusal, Evan and I realized that we have the same object in hand. So we had arrived at the same object from two different directions. And then it seemed to us that this must have some universal nature, right? And we combine forces to do the work that I'm describing to you right now. So here's a simulation of the stationary horizon. So those individually colored paths, they are Brownian motions with drift. So the guys that go to the up and right, they have a positive drift, and the guys going down right have a negative drift. The interesting feature is that any two pair of paths, they coincide for some non-trivial interval around the origin, and then they separate. So here, for example, you can see a separation point. So the blue and the yellow would be running together from the origin, and then they separate. And the same happens in the other side. See, here the blue and the yellow separate after a while coming out of the origin. So it's a coupling. So this process is a coupling of Brownian motions with drift, and the drift is the index of the process. So in the literature, one finds various sorts of couplings of Brownian motions with drift, but this one doesn't. We haven't at least found it before in any older literature. All right. So that's the stationary horizon. And now I can state for you the theorem, the invariance theorem. So run now the KPZ fixed point by taking this stationary horizon thing as the initial data. So for each value of xi, let it evolve under the KPZ fixed point. And then we have the invariance, the distribution is preserved. And we also have a uniqueness statement. So this gives the unique joint invariant distributions, for example, not for example, but specifically under a condition on the asymptotic slope.
Timo, can you hear me? Yeah,
Yes,
I have a question on your, it's basically on the previous picture. If you take a finite x,
yep,
and if you look at all the possible values of g psi of x for, say, psi in an interval, do you know if this is finite or not?
Sorry, if what is finite?
The set of values that...
Oh, no, it goes all the way to, it's unbounded, yeah.
No, but if you take a bounded interval for psi, say psi in -1, 1.
Oh, psi minus 1, 1. Oh, then it's finite. Yeah.
Okay, so it's finite, okay.
Yeah, so right. So to say, yeah, thanks for actually, I should have said this. So if you, for example, fix x value 0.2 here, and you go across here vertically, what you see is a jump process. So in any finite interval, you have finitely many jumps. We have some information about that process, some formulas for distributions, but we don't have a completely good picture of where it's coming from. That's one of the, so we have various information about this object, but not complete yet. Thanks for the question. That was an oversight on my part.
Thank you.
Highlight that. Anything else at this point? All right. So we have this invariance.
Just ask a question, maybe.
Yeah.
So this object looks a little bit like the Brownian web, right? But it should be very different, no?
Yeah, it must be different. Yeah, because the paths, once the paths separate, not only do they never meet again, but their difference is monotone increasing. So it has quite a bit of rigidity in a way. Yeah.
Yeah. Okay.
Right. So I was in the middle of this theorem here. We have invariance, we have uniqueness, we have more. So I'm giving you just a part of our theorem. We have also attractiveness. And we don't have to be in the space of continuous functions. Upper semi-continuous is okay. How we prove this? We prove this with discrete approximations. That's a little bit disappointing. It would be nice to develop the right stochastic analytic tools for studying this thing, instead of going back to discrete approximations and then taking limits. But that's how it is presently. And I want to say that ours is not the first result in this direction. So Leandro proved earlier the case of a single function. He proved invariance and attractiveness under a slightly stronger condition than what we have here. Okay, so that's the invariance theorem. And now from that follow this key point that we're really interested in, namely that if we look at the Busemann process on a fixed time level, then that's distributed exactly like the stationary horizon. So now I want to go back to the geometry and try to draw some consequences from this. So earlier, there was the hint that the jumps of the Busemann process have some significance. So let me give a name to that set. Here it's capital Xi. And here's some properties of it. This set is countably infinite and dense. It's a random set, of course. Well, I guess not of course, but it is. It's countably infinite and dense. And it's sort of present all over the place. So what the second line says here, I'll just say it in words. It's much better to understand that way. Fix any t, any time level t, then you'll see the full set of jumps in the Busemann process across that time level. And if you ask about the probability of a fixed direction lying in that set, then that probability is 0. Now, those of you who are familiar with the exponential corner growth model and its competition interfaces and geodesics, you'll recognize that this picture is exactly the same as in the exponential corner growth model. Similarly, there is a dense set of exceptional directions and all that. But then when you go and talk about the geodesics, things get a little bit different, because in the continuum, there's a lot more room for mischief. So there's my capital Xi set again. So now let me make two statements here. What it entails for a direction to be a member of that set or not. So a good Xi is one that is not in the capital Xi. And in that direction, all the semi-infinite geodesics coalesce. But in distinction with what happens to the lattice, there's still non-uniqueness. So there are still at each level countably infinitely many points from which there are two Xi-directed geodesics. So these geodesics, they separate immediately, but then they come eventually together because the coalescence holds. So they form these kind of little bubbles there. So this does not happen in the exponential corner growth model. And then in the exceptional direction, there is not complete coalescence, but instead there are two families of coalescing semi-infinite geodesics. But what we don't know presently is whether there are more than two. Again, this is something we do know in the exponential corner growth model. In the exponential corner growth model, in every exceptional directions, there's exactly two trees of geodesics that are distinct, but they go in the same asymptotic direction. So here at the bottom are two pictures. The first picture illustrates the first alternative. There's coalescence. The second picture illustrates the second alternative. So from each point, eventually there are two Xi-directed geodesics, which there's the separation point there. But then there's coalescence in this family, this blue family over here, and this red family over here.
I have a question.
Yes.
So if this horizon, it's somehow derived. I mean, it's related to a scaling limit of the corner growth. So can you explain why this property of the corner growth model does not transport to the scaling limit?
Which property?
This thing about the coalescence of the geodesics. Like,
Why it doesn't translate? Well, I should say that this is we don't know this now. We don't know if there's more than 2 families. So it's unknown. On the other hand, see, the stationary horizon only captures what happens on a single time level. It doesn't sort of capture the whole. It doesn't capture the entire geometry in the plane. So I don't think I can give a satisfactory answer to your question, to be honest. All right.
Thank you.
So I want to show you one more result about directed landscape, and then I'll shift gears and go to TASEP. So here's what we call the Busemann difference profile. So this function here, this j, it vanishes, of course, identically if you take one of the good directions xi, but take one of the exceptional ones, and then this function is non-decreasing. It vanishes in a neighborhood of the origin, but then after a while it becomes positive to the right, negative to the left, and then it just keeps growing. I want to say something about its distribution. Let tau xi be the point on the right where it lifts off from the origin. Now it's a little bit subtle now, right? Because any particular xi value is exceptional with probability 0. So in order to say something, we have to condition. So we condition on these xi values being exceptional in the POM sense. This sense coming from the theory of random measures. I cannot pause to explain what it means, technically speaking, but it is a conditioning. And the interesting fact is that if you condition like this, then this Busemann difference profile is actually a version of Brownian local time. And the same thing happens to the left. So you can define the counterpart of the tau to the left, and you can look at the function to the left, and you get 2 independent versions of Brownian local time. So here's a picture of that. You see at the origin, this function vanishes in an interval that's there. And then it starts evolving like a Brownian local time to the right and another Brownian local time to the left. And this is not the end of the story. We can say some things about what this means geometrically, but I think I'm going to skip that now because I'd like to be able to say something about the TASEP speed process also before my time is up here. So that's the end of the directed landscape portion. And I'm now going to transition into TASEP, which I think is a beloved object for a number of people in the audience. I'm going to start by introducing this version where we label all the particles and we run the dynamics with some priorities. So in the picture there is the initial state. I'm on the one-dimensional lattice Z. I've filled every site with a particle. Each particle has its own label. And initially at time 0, the label of the particle matches its location. So those numbers, those circles are the particles, and the numbers in the circles are the labels of the particles, and then underneath the number line are the signs. And we attach Poisson clocks to each edge. And when the edge fires, we rearrange the particles, if necessary, so that after the jump, the lower label is on the right and the larger label is on the left. Okay? So the lower label particles drift to the right and the higher label particles drift to the left. Right? So that's TASEP with priorities. And let's simulate here a little bit just for fun. So the red star here marks the ring. So when that edge there rings, the 1 and the 2 change places. And let's say there's a ring now there between sites 0 and 1. That clock ring switches around 0 and 2. And one more ring over there, 0 and 1 switch places. And here's a ring that does not do anything. When the clock rings here, see the particles with labels 2 and 1, they're already arranged in the correct order. So there's no jump there. All right. So I hope the dynamics is at least fairly clear. I want to take a limit in this picture now. So I'm going to reverse my point of view. Instead of indexing the label of the particle at a particular site, let me index like this. Let xj be the position at time t of the particle with label j. And the fundamental theorem here is that all these limits exist almost surely. So each particle has a limiting speed. I'm calling it u sub j. So this bold red u will be this value for the rest of the talk. They're uniformly distributed. They're, of course, wildly correlated, right? But individually, they're uniform. And this is the definition of the Taset speed process. So what do we know about it? Immediate properties. It's ergodic under translations of the lattice. And it's also stationary under the Taset dynamics. So what I mean here by Taset dynamics is exactly what was in the previous slide. Whenever an edge rings, you rearrange the values if needed, so that the smaller value is to the left, to the right, and the larger value to the left. So this result comes from a series of marvelous papers, beginning with Ferrari Kipnis 1995, and then 2011, Amir, Angel, and Valko were the ones who combined those limits into the speed process and studied its properties. Okay. So let me say a few things about the speed process next. So it's a pretty complicated object, but certain projections are very simple. So fix a number rho and declare eta j to be 1 or infinity, depending on the value of u, but make it monotone like I made in that formula. The claim is that this eta sequence is actually IID Bernoulli. And I can prove it without any calculation. So if you think through the pathwise evolution, you realize that it commutes with any coordinate-wise non-decreasing map. In other words, the eta values obey the same kind of dynamics, and of course are stationary for the same kind of dynamics. So then classic Liggett says that this has got to be Bernoulli, since it's also spatially ergodic. And even more is true if you take any non-decreasing function of these u values, then what you obtain is one of the translation ergodic stationary distributions for multi-class Taset, which were described by Pablo and James Martin in their 2007 AOP paper. So this fact is of importance for what comes next. Now, I want to find the stationary horizon lurking somewhere here in the Taset speed process. How do I scale it to get to the stationary horizon? Well, the clue is what I just showed you. These projections are IID Bernoulli, so they're basically Brownian motions. So if I take one of them, I center it appropriately, scale it, I go to a Brownian motion. So that's what we'll do. We'll take these sort of height functions of the speed process, we'll scale them appropriately, and we put them all together, and this will be the stationary horizon. So here's a definition. It's a little bit of a mouthful, but you take any centering V, and then you define this process here. In this sum, you see the increments, the indicator functions that are the sort of the height function of these u values from the speed process, and you center appropriately, you scale appropriately, and this is the process that will converge to the stationary horizon. Now, I'm lying to you a little bit here because I want to try to convey what's really going on and minimize formulas. So this sum makes sense if the upper summation limit is an integer. If it's not an integer, interpolate so that you make this continuous in the x variable. And I want this to be by infinite in x, so there's the corresponding definition for the negative x's. This is the positive x definition. So I think that most of you will see what I mean here. Now, this, by the way, is a very familiar thing. This is the way you convert Taset particle configurations into these sawtooth interfaces. So it's just the same formulation, right? there are these various constants floating around now. I chose them specifically so that if you fix the parameter xi and you look at it as a process in x and you take the limit as n goes to infinity, you get again these Brownian motions with drift. And in what space does this object lie? It's again in that D space with states in the space of continuous functions. So if you look at this, look at how the xi parameter here enters into the indicators. As the xi increases, there's a point at which this indicator switches from 0 to 1. So you get these cadlag jumps right there. Okay. All right. So let's take a limit of this guy. So there, I'm just repeating the definition again for you to see. Take a stationary horizon, and the theorem is that you have this convergence on the path space D. How do we prove it? A bunch of technical calculation. The key idea that is all over the place is the Ferrari-Martin queuing representation of the projections. So if you remember still, the stationary horizon was built with queuing mappings. The queuing construction of Ferrari-Martin becomes in the limit the queuing construction of the stationary horizon. And you know, then you fill in the details as you can imagine. Okay. As the last thing, I want to now connect the speed process with the directed landscape, because now they both have in common the stationary horizon thing. So let me just here remind you of the last few things about the directed landscape. We have the Busemann process on a fixed time level. It has the distribution of the stationary horizon. We have the difference profiles in the exceptional directions, which under palm conditioning were Brownian local times. So now what I want to show you is how the TASEP speed process approximates these features of the directed landscape. I think that's sort of interesting in a qualitative way. So the speed process has the following interesting feature. Even though the individual values are uniform, they're far from all distinct. In fact, there's lots of repetition among them. So Amir, Angel, and Valko introduced this notion of a convoy. So a particular speed process value um has a convoy, which is just a set of all indices where you see that same value. And they proved that these guys are renewal processes. They're zero density renewal processes. Okay. So recall again the scaling of the speed process. There it is. And let's define a difference function here also. So let's take the h at xi and subtract the h at xi minus. So we're capturing the jump here. Look at this indicator here. Where do you see a jump? You see a jump exactly when xi picks up a particular value that you can algebraically deduce from this expression here. And here I've spelled it out for you. This function is non-zero if and only if the xi value lies in this set of scaled and centered speed process values. Okay. And suppose that xi is one of those values. Sorry, the formulas get a little hard to follow so fast. But if you do manage to trace this through, then if my xi is one of these values, then what is the difference function j? Well, it becomes exactly a sum of the indicators of where the uj value coincides with the um value. In other words, it's counting the scaled cumulative convoy. Okay. So in other words, the exceptional directions of the directed landscape are approximated by these centered and scaled speed process values, and the Busemann difference profiles are approximated by the convoys. So now I just want to state a last theorem where I make this connection somewhat precise. Those are just reminders of the definitions I wrote down a moment ago. So here's a theorem. This theorem is correct in spirit, but not technically, and I'll tell you in a moment how it's not exactly correct. But in spirit, the result is that if you form this simple point measure of these xi values that come from the scaled speed process, and then the difference functions, then this simple point measure converges in the vague topology in distribution to the corresponding object in the directed landscape, where you have the exceptional directions and the Busemann difference profiles. Now, the reason that this is not quite rigorously correct is that these sets here are not discrete. And if you want to do vague topology on point measures, you should have discrete sets. So you have to fix this a little bit. And in the paper, we fix it by adding a third component inside here, which just spreads out the values so that you have a legitimate point measure. All right, I've come to the end of my talk, and thank you very much for your attention.
So let's thank Timo for a very entertaining and interesting talk. Could I open the floor for questions, more questions? Maybe I could ask a question just to get it started. So you mentioned that you're using discrete approximations to show the formulas for the stationary horizon before. Given the Markov property and things like that, can one write down a transition function or a generator and then see invariance of the stationary horizon from that kind of formulation?
Yeah, I don't know. I don't know. Yeah. That would be, yeah, from some people's background, that would be a natural thing to do, right?
Yeah, no.
To me, that would be scary.
No,
that would scare me. But yeah, you might try. Yeah.
No, it's scary for me as well. So, I see. Are there other questions?
Timo, this is Pablo. I am curious about these convoys because the distance between two particles in the convoy is finite if you have one particle in the origin, but has infinite mean, right?
Yeah.
So how can they survive to these limits?
Well, I think it's in the scaling. So, I mean, it's like they sort of they sort of come like roughly like zeros of a random walk, right?
Yeah.
So if I add up, if I look at n places, I have roughly square root n hits. So then if I divide by square root n, I should get something order 1.
Okay. So do you have any you know that there is a square root of n, the distance?
Yeah, I think it's in Amir Angel Valko. Yeah, I think it's there. Yeah, they have pretty sharp results about convoys. Yeah.
Okay, thank you.
Yeah, see the random walk thing comes from the queuing representation. The queues are totally underneath everything there.
Well, this in some sense these are the unused times of the queue, right?
Exactly. Yes, exactly. Those. Yes, that's exactly what they are. Yeah, they are the unused services. Yeah.
Okay. Thank you, Timo.
Yes. So I was wondering. So this scaling limit of the convoy, it's the difference between two. Well, it's the difference between the Busemann at psi plus and the Busemann at psi minus. So this is the local time of a Brownian motion.
Yeah.
So is the convoy set, does it correspond to the zeros of the random walk, or it's just something like the zeros of the random walk?
Let's see. I think, yeah, okay, I can't remember exactly, but it may be, yeah, I think, Pablo, do you remember? I think there's actually sort of a lazy random walk, and it's exactly the zero set of.
Yeah, I think that you have a queue, critical queue.
Yeah.
So that and you condition to have a zero to be empty at time 0, and then you have an excursion, and then the next time that you are empty is like a 0. In fact, yes, something like that. I think. Yes.
Thank you.
Thank you, Timo. Yeah.
Well, if there are no further questions, why don't we thank Timo again for a very nice talk. Thanks, Timo,
Thanks
for coming on.
Thanks for the opportunity. Thank you for the opportunity, and yeah, hope to see some of you soon enough.
I hope so.
Okay, goodbye, everybody.
Bye.
Bye-bye.